Are you sure you're not secretly sabotaging your Power BI models before they even get off the ground? Most professionals don't realize a single bad decision during data modeling can derail their entire project. Stay tuned, because by the end of this video, you'll know exactly why these common pitfalls exist and how a simple tweak can completely transform your reports faster and more reliable than ever. The chaos of raw data. Imagine staring at a massive spreadsheet with endless rows and columns. Where do you even begin? It's overwhelming, right? Data pours in from multiple sources, and each source seems to speak its own language. Different formats, terminologies, inconsistencies, it all adds up to a chaotic starting point. Raw data, while valuable, often arrives as unstructured information that makes your job harder rather than easier. The problem is, when we skip the step of organizing and modeling data up front, the entire process that follows becomes unnecessarily complex. Unstructured data makes things confusing right from the start. Imagine trying to make sense of thousands of rows with duplicate entries, mismatched column headings, or missing values. These issues not only slow you down, but also increase errors, which can mean decisions based on inaccurate information. Think of a situation where customer data from one table doesn't align with the sales data in another. It's frustrating, right? And because the data isn't structured, Power BI, or any tool for that matter, won't automatically know how to join the pieces together. That's the challenge many users face when they open Power BI for the first time, importing raw data as is and expecting instant results. This confusion leads to another frequent frustration: reports that don't make sense or take forever to load. If the data isn't properly structured, reports can return odd figures like totals that don't match expectations, incorrect trends, or summary values that simply don't add up. This happens because the model underneath, the foundation of everything you're building, is flawed from the beginning. Poor performance is another symptom. Have you ever built a report only to notice it takes forever to refresh? It's often because the underlying tables are unnecessarily large or filled with repetitive, irrelevant data. The result is wasted time, not just when analyzing reports, but throughout the entire business decision-making process. Teams rely on insights from these reports, and when they're slow or misleading, the ripple effects can impact entire projects. This all boils down to one crucial fact: unorganized data will continue to create chaos unless you approach it with a clear plan. That's where a structured approach becomes vital. Instead of importing data blindly, the first step in Power BI should always revolve around making sense of what you have. This isn't just about cleaning data, although that's part of it. It's also about organizing it in a way that aligns with your goals. You need to think about how different data sources interact, which pieces are relevant, and how they can come together in a meaningful way. Skipping this step is one of the most common reasons Power BI models fail before they even begin. This is where data modeling emerges as a solution. Data modeling is the process of shaping your unstructured data into something logical and efficient, bringing clarity to what was complete chaos. It's not just a technical task, it's an essential planning step that ensures every data point in your model supports your analysis. The core idea is to organize your data into a structure that Power BI can easily process and analyze without excessive repetition or unnecessary complexity. Here's something to think about. When your data is organized correctly, you're no longer guessing what goes where or why your relationships aren't working. Instead, you're in control, and you can design reports that are not only faster but far easier to interpret. The messy, overwhelming chaos becomes something you can work with, manage, and actually use to drive decisions. That's the power of modeling your data properly. Now, the big question is how to begin bringing order to the chaos. The good news is you don't have to figure it all out at once. Data modeling breaks the process into manageable steps. It relies on a few foundational tools, most importantly fact tables and dimension tables. These tools form the backbone of an efficient Power BI model and serve as your guides for turning messy spreadsheets into streamlined reports. By understanding how to use these properly, you can start taming the chaos step by step. Think of a fact table as the central hub of your data. It's where all the measurable events are recorded. Sales transactions, website visits, or inventory changes all live here. This table is your starting point for analyzing trends, making projections, or digging into the numbers. But a fact table alone doesn't tell the whole story. Numbers without context don't get you far, which is why dimension tables are just as important. These tables provide the context behind the numbers: customer demographics, product categories, dates, and more. By following this structure, you can ensure your data model not only makes sense, but also performs well. Every table has a purpose, relationships between tables are clear, and your reports don't just work. They're reliable, fast, and insightful. When data modeling is approached correctly, the time and effort you save later down the line more than compensate for the planning required upfront. To sum it up, starting with a solid data model is absolutely critical for success in Power BI. It's the only way to bring clarity and control to the messy, chaotic data you're working with. Without this foundation, it's almost guaranteed that your reports will be slower, less accurate, and harder to sustain over time. But by laying the groundwork now, you're setting yourself up for smoother, smarter reporting in the future. In the next part of this video, we'll dive deeper into the tools that make data modeling possible. Specifically, we'll focus on fact tables and dimension tables. These two concepts are the building blocks of any great data model, and understanding them is key to everything that follows. So let's take a closer look at how these tools can guide your transformation from chaos to clarity. Fact tables, the core of your data. What if I told you all your data boils down to one central story? That's exactly what a fact table represents. It's the heart of your data model, the main character around which all the supporting details revolve. The fact table holds the measurable events or transactions that are at the core of your analysis. It's not just a list of data points. It's the structured foundation that enables meaningful insights. Whether you're tracking sales figures, website visits, or inventory movements, the fact table is where these real-world activities are captured and stored. But here's where things often go wrong. Many Power BI users either overload their fact tables with too much information or leave out critical details, producing an incomplete picture. Let's talk about the first issue, including too much information. A fact table isn't meant to hold every possible attribute of an event. For example, think about a sales transaction, including fields like product descriptions, customer email addresses, or detailed shipping notes. In the fact table might seem logical at first, but it bloats your model. This creates redundancy, increases storage requirements, and slows down query performance. Instead, a fact table should focus on essential measures, like sales amounts, quantities, or costs, and use foreign keys to reference relevant attributes stored in dimension tables. By keeping only what's necessary, you make your model more efficient and easier to manage over time. On the flip side, a common mistake is not including enough detail in the fact table. Imagine a sales fact table where the only recorded metric is the total sales amount. While this might work for some high-level analysis, it severely limits what you can do. You can't drill into performance by product, by individual salesperson, or by geographic region because the granularity isn't there. Granularity in this context refers to the level of detail captured by each row of the fact table. If your table is designed at the transaction level, it records details for every single purchase. But if it's summarized at, say, the daily or monthly level, much of that detail is lost. Choosing the right level of granularity upfront is critical because it directly impacts the types of questions your model can answer. Let's ground this in a practical example. Say you're working with a retail sales fact table. If the granularity is set at the transaction level, each row could represent a single purchase by a customer. Columns might include a transaction ID, date, product ID, customer ID, quantity sold, and total price. Keeping the model tall and narrow like this ensures efficiency, as these columns are primarily numeric or reference foreign keys. But what happens if you aggregate this table to record total sales by day? Now, you lose the ability to drill down into product-level details or track individual purchases. Worse yet, combining too many levels of aggregation into the same fact table, say daily totals alongside individual transactions, leads to inconsistency and confusion. This isn't just a theoretical discussion. Poorly designed fact tables lead to real-world issues. They can make analysis harder by mixing levels of granularity or overlaying unnecessary details. They also affect performance. Larger tables with redundant or overly detailed rows slow down your model and make it harder to get quick, reliable results. Every column and every row you include in your fact table should serve a specific purpose. If it doesn't, it probably doesn't belong there. So, what should a well-designed fact table look like? At its core, it should do two things well: represent measurable events in a concise way and link those events to rich contextual details through dimension tables. For example, a typical sales fact table could include metrics like the sales amount, the units sold, and discounts applied. Each transaction is represented in a single row, and foreign keys, like the product ID, the customer ID, or the store ID, point to dimension tables that provide more information about these entities. This structure keeps the fact table lean while still enabling detailed analysis through its connections to other tables. The design of the fact table has to align with the questions you want to answer. In a retail context, are you trying to track sales trends over time? Then make sure your fact table includes a date reference. Are you assessing product profitability? Ensure your fact table captures cost data alongside sales revenue. Are you tracking regional performance? Then store location information as a foreign key linked to a geographic dimension table. These decisions should be guided by your analytical goals, as well as by practical considerations like storage optimization and performance. The power of fact tables becomes evident when paired with Power BI features like aggregation and filtering. For instance, say you want to see total sales by month. Because your fact table records each transaction, Power BI can easily calculate these totals by grouping data at the monthly level. Want to break this down further by product category or region? No problem, as long as those attributes are stored as foreign keys pointing to dimension tables. This flexibility is why fact tables are at the core of every robust data model. They provide the raw metrics necessary for analysis, but in a structure that's optimized for performance and clarity. Contextualizing this further, you'll see fact tables at work in industries across the board. In e-commerce, fact tables capture details about customer orders, items purchased, prices paid, discounts applied, and shipping costs. In healthcare, they track patient visits, medical procedures, and associated costs. In manufacturing, they record production volumes, defects, and operational runtimes. In all these examples, the fact table serves as the backbone for analytics, enabling organizations to monitor key metrics and identify trends over time. Now, let's connect the fact table to the broader structure of your data model. If we think of the fact table as the main character, then dimension tables act as the supporting cast, adding depth and context to the numbers in the fact table. Without dimension tables, your fact table becomes flat, just a collection of raw numbers without meaning or explanation. For example, without dimension tables, you might see sales totals but have no information about what products were sold or where the sales occurred. Dimension tables bring this missing context to life. When structured properly, fact tables and dimension tables work together to form the foundation of an efficient and scalable data model. Queries run faster, reports become more intuitive, and your analysis can adapt as requirements change. The benefits of a well-constructed fact table ripple through the entire process, saving you time and reducing frustration down the line. In the next section, we'll dive deeper into dimension tables, what they are, how they complement the fact table, and why they're critical for your data model. After all, numbers alone rarely tell the full story, and dimension tables are how we add that much needed context to make data truly actionable. Stick around to see how these two elements, fact tables and dimension tables, come together to form the foundation of a simplified yet powerful data model. And dimension tables, adding context to your data. Why do numbers alone rarely tell the full story? Let's think about this for a second. Standalone numbers like total sales, website visits, or customer transactions can seem meaningful on their own but lack something critical. Context. Take sales data, for example. Knowing that your business made $1 million this month can feel like a solid win. But without knowing which products sold, the regions where performance was strongest, or what types of customers contributed most to that success, your analysis remains incomplete. This is where dimension tables come into play. They add the context needed to turn raw numbers into actionable insights, serving as the supporting cast to your fact table's measurable events. Let's break down what dimension tables do. A dimension table describes the who, what, where, and when within your data. While a fact table handles the how much or how many, the dimension tables connect those measures to meaningful attributes. For example, your fact table might track a sales transaction, showing that $500 of revenue came from a specific transaction. But how do you know what product was sold, who the customer was, or when the transaction occurred? A dimension table provides this information, making your data more understandable. It allows you to filter, categorize, and group the measures stored in the fact table in ways that help you answer business-critical questions. Here's an example. A product dimension might include attributes like product name, category, brand, and color. When paired with a fact table capturing sales amounts, this dimension table enables you to analyze performance by product category or brand instead of just looking at raw numbers. Similarly, a customer dimension table containing details like customer demographics, age group, or region lets you assess how different customer groups are contributing to sales or engagement. Dimension tables are designed to summarize and organize information in a way that's intuitive for both you and Power BI. Now, one of the most common frustrations arises when dimension tables are incomplete or poorly designed. Let's say your product dimension doesn't include product categories or subcategories, only product IDs. In this case, your analysis is limited. You might be able to track performance for a specific product, but can't easily roll that up to a broader category, say electronics or kitchen appliances. Or think about a customer dimension that's missing geographic information. If you only have a customer ID and no data on location or demographics, you've lost a critical piece of insight. These gaps don't just make reporting harder, they can cause you to miss trends you'd otherwise catch. This is why designing thorough, well-thought-out dimension tables is essential for successful analysis. Dimension tables typically have a few key characteristics that set them apart from fact tables. First, they're descriptive, rich with attributes that explain the numbers in the fact table. Second, they're often wide, meaning they contain many columns. Each column provides additional details like product names, customer demographics, or time periods, allowing you to slice and dice your data in countless ways. Third, and perhaps most importantly, they are built to provide context without redundancy, instead of including this contextual data in the fact table where it will be repeated for each transaction. It's consolidated within dimension tables. This structure keeps the fact table lean while ensuring all the necessary details are still accessible. Think of an example where you're analyzing sales over time. A well-designed date dimension lets you break down performance by year, quarter, month, or even specific days. It might also include flags like is holiday or is weekday, helping you quickly filter and group data to spot trends. Without this dimension, you'd have to manage dates manually or rely on Power BI's default tools, which often lack flexibility and customization options. By taking the time to build a proper dimension table, you're not just saving time, you're ensuring your analysis is as accurate and actionable as possible. Likewise, a geography dimension can make location-based analysis far more effective. Let's say your business operates in multiple regions. A geography dimension might include attributes like country, state, city, or even zip codes. With these attributes in place, you can easily compare performance across regions, identify high-performing areas, or investigate where sales might be lagging. Now, imagine that a customer is included in your fact table, but their address is not linked to a detailed geography table. Without that geographic context, broader regional analysis becomes challenging, if not impossible. A dimension table can also handle more advanced needs, like tracking changes over time, using the concept of a slowly changing dimension. For example, what happens when a customer updates their address or when a product is reclassified into a new category. In these cases, a dimension table can use attributes like start and end dates to track the validity of each record over time. This allows you to perform analysis based on historical attributes rather than overwriting important data every time something changes. Features like surrogate keys, a unique identifier assigned within the dimension table, are helpful for managing these changes while maintaining clean relationships in your data model. Dimension tables aren't only relevant to highly technical use cases, they also make your reports more intuitive for anyone using them. When your table includes natural attributes like product names, customer groups, or fiscal year, end users can quickly understand the insights being presented without having to dig through codes or raw numbers. This is especially helpful when sharing Power BI reports with others who might not be as familiar with the underlying data. Offering descriptive, easy-to-understand tables allows stakeholders across your organization to interpret and act on insights more effectively. Let's take another example, a campaign dimension table. This would include details about marketing campaigns, such as campaign names, IDs, start and end dates, and types, email, display ads, etc. With this table connected to your fact table, you can analyze the effectiveness of each campaign, looking at metrics like total revenue generated or customer acquisition rates. This type of analysis is crucial for improving marketing ROI and optimizing future campaigns. Dimension tables also help with filtering and organizing data in Power BI. By linking dimension tables to fact tables through relationships, you give Power BI the structure it needs to filter data efficiently. Want to compare revenue by product category? Simply select a filter from your product dimension, and Power BI will automatically adjust the numbers in your report based on the relationships you've defined. Similarly, you can use slicers or filters tied to dimensions like date or geography to drill into specific areas of interest. This interaction between dimension and fact tables is what powers the dynamic, responsive reporting capabilities that make tools like Power BI so powerful. Ultimately, a well-designed set of dimension tables simplifies your analysis process and opens up deeper insights. When these tables provide the right level of detail, combined with thoughtfully chosen attributes, they help you move beyond surface-level reporting. You're no longer limited to just knowing the what. With dimension tables, you can answer the why and how, opening the door to strategic decision-making. Cleaner models lead to faster queries, clearer reports, and better outcomes at every level of your analysis. Dimension tables are the essential complement to fact tables, but together they're not enough. To truly benefit from these structures and maximize performance, they need to work within an organized framework. This is where the star schema comes in, serving as a roadmap to simplify your model and make it more efficient. The star schema lays the foundation for how dimension tables should be connected to fact tables, ensuring clarity, speed, and scalability. Next, we'll explore how these elements come together in the star schema model. You'll learn why this structure is the gold standard and how it transforms your Power BI model into a well-oiled machine. Keeping your model structured isn't just about aesthetics, it's about ensuring the whole system runs smoothly and efficiently. Make sure you stick around to see how the star schema brings it all together. The star schema, a roadmap to efficiency. What's the simplest way to organize your data for speed and clarity? The answer is the star schema. It's a straightforward yet powerful way to structure your Power BI models for better performance, easier maintenance, and more intuitive reporting. If you've worked with complex or slow reports before, there's a strong chance the data model wasn't optimized. And skipping the star schema is often the cause. Let's break it down so you can see why this structure is considered the blueprint for an ideal data model. At its core, the star schema is a way to arrange your data into two main types of tables, a central fact table surrounded by a set of dimension tables. The structure gets its name from the way it looks, a star. The fact table sits at the center, holding the measurable events or transactions such as sales or inventory levels. The dimension tables act as the points of the star, each one giving context to the measures in the fact table. Examples of dimension tables include product details, customer demographics, or date information. This logical organization makes it much easier to analyze your data and draw meaningful insights. To understand why this matters, imagine skipping the star schema. Without it, your data might resemble a flat table or a different type of schema, like a snowflake schema. In a flat table, you could have all the details, transactions, customer information, product details stored in one single table. At first glance, it might seem more convenient since all the data is in one place. But larger data sets quickly become unmanageable with this approach. These tables grow unnecessarily large due to repetitive information. For instance, every transaction would have repeating product descriptions, customer names, or other attributes in multiple rows. This increases storage requirements and worsens query performance. On top of that, flat tables are harder to navigate and maintain, especially if you're dealing with hundreds of columns or millions of rows. Now, let's compare the star schema to another approach, the snowflake schema. A snowflake schema is a variation in which dimension tables are further normalized, meaning they are split into multiple related tables. For example, instead of having a single product dimension table, a snowflake schema might split product data into separate tables, one for product categories, one for brands, and one for individual products. While this reduces redundancy within the dimension tables, it introduces complexity by increasing the number of joins Power BI must process. Each additional join slows down queries, making your reports take longer to load. Simple tasks like filtering data or drilling down into details become more cumbersome because the added layers of complexity can introduce ambiguity or errors in relationships. For this reason, although snowflake schemas work in some niche cases, the star schema is the preferred approach for Power BI. The simplicity of a star schema has practical benefits. For one, it reduces the number of tables, making the model easier to understand and maintain. Instead of working with a web of interconnected tables, you have a clean structure that helps you see how data flows. Since the relationships between the tables are typically one-to-many, the dimension tables filter the fact table, which limits the data used in calculations. For example, a date dimension can filter your sales fact table to show only figures from the current month. This is what makes reporting in Power BI both dynamic and responsive. Filters applied to dimension tables automatically propagate through the fact table. Because the fact table in a star schema holds only the essential measurable events and links out to external context stored in dimension tables, you avoid redundant data entries. This improves storage efficiency and speeds up queries. A real-world example would be comparing a flat table to a star schema. In one test, a flat table model was 34 megabit, whereas a star schema model was only 6.5 megabit. This dramatic size reduction wasn't just good for storage, it also made the model perform faster. Optimizing performance is especially important for large datasets, where even small inefficiencies are magnified. The star schema also helps solve relationship issues that often arise in poorly designed models. For example, many-to-many or bidirectional relationships can slow down performance or create ambiguous results. These issues stem from unclear connections between tables, especially when cardinality, meaning the number of unique values in a column, is high. Bidirectional filters can introduce filtering loops that cause calculations to return incorrect results. The star schema eliminates this problem by structuring tables with clear, one-directional relationships, ensuring filters flow logically from dimension tables to the fact table. A practical example of how a star schema improves performance involves aggregations. Say your sales fact table originally contains 210 to 500 rows, with each row representing an individual transaction. Aggregating this data into totals by month reduces the row count significantly, perhaps down to 1,794 rows, without losing the level of detail you need for most visualizations. Querying fewer rows means faster load times for your reports. This kind of efficiency is built into the design of the star schema. Another benefit of the star schema is how it simplifies time-based analysis. A properly designed date dimension table allows you to easily filter and group data by days, months, quarters, or fiscal periods. Without this, you'd be relying on Power BI's auto-generated date tables, which can consume unnecessary space and lack customization features. By replacing automatic date timetables with custom ones, you gain more control over your time-based metrics, enabling powerful analyses like comparing year-over-year growth or identifying trends during specific periods. By keeping your dimensions clean and well organized within the star schema, you make reports far easier to navigate. For example, if someone wants a report showing total sales by city, the geography dimension table in a star schema allows you to filter sales data down to specific countries, regions, or cities in just a few clicks. This flexibility is much harder to achieve with schemas like snowflakes, which require you to join multiple layers of dimension tables just to access the information you need. The benefits don't just stop at clarity or ease of use. A star schema actively contributes to better compression in Power BI's data model. Columns with low cardinality, like product categories or fiscal quarters, compress much more efficiently than columns with high cardinality, such as unique transaction IDs. This is why it's essential to design your dimensions with the right level of detail. For example, instead of storing full date time stamps in your fact table, you could split these into separate date and time columns. Doing so reduces cardinality, saves memory, and speeds up queries, all without losing meaningful information. When implemented correctly, the star schema supports better DAX performance too. By simplifying the structure of your data model, you reduce the complexity of DAX expressions, making them easier to write and faster to calculate. For example, creating measures such as calculating total sales or average revenue per customer becomes more efficient because the relationships between the tables are straightforward and the data is already well organized. Whether you're a beginner or an experienced Power BI user, this simplicity allows you to focus less on troubleshooting and more on deriving insights. It's worth noting there are situations where the snowflake schema might seem appealing. For instance, when working with highly normalized data from a source system, the snowflake structure can reduce redundancy within your source data. However, this benefit comes at the cost of performance and increased complexity. In Power BI specifically, the goal isn't normalization, it's optimization. The star schema reduces unnecessary joins and prioritizes speed and clarity, which are critical for end users who need insights quickly. In short, a star schema isn't just a nice to have. It's essential for building efficient and scalable Power BI models. It reduces the size of your data model, makes relationships clear and logical, and ensures queries run as efficiently as possible. The visually intuitive structure also makes it easier to explain your model to others, especially if they need to maintain it in the future. But what happens when the star schema is abandoned in favor of the snowflake schema or other designs? This decision often leads to sluggish performance, confusing relationships, and harder to maintain models. While snowflake schemas have their place in certain scenarios, the added complexity usually outweighs the benefits, particularly in Power BI. That's why adopting the star schema is one of the most impactful choices you can make when designing your data models. In the next section, we'll explore the snowflake schema in more detail. We'll discuss its potential pitfalls, why it's often unnecessary for Power BI, and the rare scenarios where it might make sense. If the star schema is the roadmap for efficiency, then understanding the snowflake schema helps you recognize when complexity backfires. Stay tuned to see how you can avoid these traps and keep your models simple, fast, and reliable. Snowflake schema when complexity backfires. Could overcomplicating your data model be holding you back? It's a question that's worth asking, especially when you hear about something called the snowflake schema. While it might sound technical and even useful in certain situations, the reality is that a snowflake schema often introduces unnecessary complexity that can drag down your Power BI model's performance and usability. Let's take a closer look to understand what this schema is, how it compares to the more common star schema, and why it's usually best to avoid unless absolutely necessary. So, what exactly is a snowflake schema? At its core, a snowflake schema is an extension of the star schema, but it adds additional levels of normalization to the data. Instead of having one central fact table and multiple dimension tables directly linked to it, some of these dimension tables are split into multiple related tables. Consider this example. In a star schema, you might have a product dimension table with columns for product name, category, and brand. In a snowflake schema, that same product dimension could be broken into 3 layers: a table for products, a table for product subcategories, and a table for categories. This multi-layered structure is what gives the schema its name, since its layout looks more complex, like the branches of a snowflake. While this approach might seem like a good idea for organizing your data, it often causes more harm than good in Power BI. One major drawback is the performance hit. Snowflake schemas require more joins between tables to return the same results as a star schema. For example, if you want to analyze sales by product category using a snowflake schema, the query must traverse multiple joins, from the fact table to the product table, to the subcategory table, and finally to the category table. Each of these joins requires extra processing power, increasing the time it takes to generate your reports. This might not seem like a big deal with small data sets, but as your data grows, the problem becomes much more noticeable. Unlike a star schema, which keeps relationships simple and direct, snowflake schemas introduce unnecessary layers that slow things down. Beyond performance issues, snowflake schemas also increase the complexity of your data model. This added complexity makes it harder to understand the relationships between tables, especially for stakeholders who need to use or maintain the model. Say you hand off your Power BI model to another team member or a business user. With a star schema, the structure is intuitive: one fact table surrounded by dimension tables with clear one-to-many relationships. On the other hand, a snowflake schema requires users to navigate multiple tables to find what they need. They might not immediately understand why there's a separate table for categories when the product table already exists. This added mental overhead increases the risk of errors, misinterpretation, and frustration when working with the data. A typical scenario where the snowflake schema might feel tempting is when your source data comes from a normalized database. For instance, imagine your company's transactional system stores data in a normalized structure where product categories and subcategories exist in separate tables. When you import this data into Power BI, you might be tempted to mimic the source system and maintain those relationships. But unless there's a very specific need to preserve the normalization, this often does more harm than good. Instead, you can merge or flatten these tables into a single product dimension table during the data preparation stage. This keeps your model simple while retaining all the critical information you need for analysis. There are, however, rare cases where a snowflake schema might make sense. One of these is in scenarios where data redundancy must be minimized. Let's say you're dealing with a multi-million row data set, and the repeated attributes in dimension tables would take up a considerable amount of storage space. In these situations, breaking a dimension table like products into multiple related tables might help reduce duplication. For example, you might separate product names, which rarely change, into one table and product categories, which are updated more often, into another. However, even in these scenarios, it's essential to weigh the trade-offs. Minimizing redundancy might save storage space, but at the cost of query performance and model complexity, something that can affect end users down the line. One potential workaround for snowflake schemas is to consider merging your related dimension tables whenever possible. For instance, if your product dimension is split into 3 tables, products, subcategories, and categories, you can combine them into one flat dimension table during data transformation. This ensures that queries only rely on a single relationship instead of traversing multiple joins. Power BI provides tools like Power Query that make this transformation easy. Remember, while flattening might reintroduce some redundancy, it often improves performance and usability, which are more critical when designing analytics models. Another thing to watch for in snowflake schemas is their tendency to increase the number of complex relationships, such as many-to-many or bidirectional relationships. This often happens when excessively normalized models require additional bridge tables to tie everything together. For example, if one dimension table links to multiple subcategories spread among other tables, you might need a bridge table as an intermediary just to define the relationships. A bridge table exists specifically to connect tables that don't have direct one-to-one or one-to-many relationships. While this can solve certain challenges, it inevitably increases complexity, slows queries, and makes the model more difficult to maintain. As a best practice, bridge tables should be a last resort and only used after thoroughly exploring simpler alternatives. The key takeaway is that simplicity should always come first when working on your Power BI models. The added complexity of snowflake schemas affects not just performance, but also design clarity. A star schema ensures that everyone interacting with the data, from analysts to business users, can easily see how the structure connects. The relationships are logical, and the simplicity directly translates to faster report generation and better user experiences. So, how can you ensure you're avoiding unnecessary snowflake schemas? One way is by focusing on the essentials during your data preparation phase. Start by asking yourself, does every table in your model serve a specific purpose? Are there opportunities to consolidate related tables? For example, instead of having separate tables for product, brand, product category, and product information, can they be merged into one all-encompassing product dimension? By proactively addressing these questions before building your Power BI model, you reduce the risks of introducing excessive normalization. If you find yourself in a situation where a snowflake schema feels unavoidable, it's crucial to carefully manage it. Keep the number of columns in dimension tables to the minimum required for analysis. This limits the number of joins and ensures the performance impact is as small as possible. Also, document your decisions and ensure all users of the model understand why the schema is designed this way. Communication becomes especially important if future teams might inherit your model. They need to know which trade-offs were made and why they exist. Using custom tools during the data preparation phase can also help mitigate the potential complexity of snowflake schemas. When gathering tables from your source system, think about transformations like joining, filtering, or appending data rather than directly importing raw normalized tables. Power BI's Power Query makes it possible to do these prep steps upfront, saving headaches later. In addition, try to define clear naming conventions for your tables and columns so that users can easily understand what's happening, even if the schema is more complex than usual. To wrap up, while snowflake schemas might seem like a logical way to maintain normalization, they often introduce more problems than they solve, particularly in tools like Power BI. Performance issues, harder to manage relationships, and increased complexity are just some of the reasons they're best avoided. In most cases, flattening your tables to fit into a star schema will create a cleaner, faster, and more efficient model that ensures better results both now and in the future. In the next section, we'll look at practical tips for designing optimal relationships within your Power BI models. You'll learn how to avoid common pitfalls like many-to-many relationships, understand why directional filters matter, and see how proper relationship design ensures everything in your model runs smoothly. Stick around because these simple adjustments can drastically improve the performance and usability of your reports. Avoiding the pitfalls of problematic relationships. Are your relationships creating chaos instead of clarity? Relationships between tables are a cornerstone of Power BI data modeling, yet they're often a source of mistakes that can lead to confusing results, performance issues, or even complete model failure. Understanding how to properly define and manage these relationships is critical for creating a streamlined, reliable, and efficient Power BI model. Let's start by breaking down what table relationships are. In Power BI, relationships connect tables based on shared fields, allowing data to flow between them. For example, a sales table might link to a product table using a product ID or to a date table using a transaction date. Relationships ensure that when you filter a report, for instance, to show sales for a specific product or region, Power BI knows how to propagate that filter through your data model. Without well-constructed relationships, your data model quickly becomes disconnected and your analysis suffers. One mistake many users make is overusing one-to-one relationships. A one-to-one relationship exists when each record in one table has exactly one matching record in another table. At first glance, this might seem harmless or even logical, but often it's a sign of inefficient design. For example, if you create a one-to-one relationship between a product table and another table containing corresponding product names due to naming mismatches, ask yourself, does this secondary table need to exist at all? Usually, data from the related table can be integrated directly into the primary table using a merge operation in Power Query or SQL. This removes the one-to-one relationship entirely, simplifying your model. Another common pitfall is the use of bidirectional relationships where filters can flow in both directions between tables. Bidirectional relationships might seem helpful in scenarios where you want multiple tables to filter one another. For example, you may set a country column in your sales table to filter a product table. But this approach can create ambiguous relationships and significantly degrade performance, especially when dealing with high cardinality fields. Filters propagating in both directions can create circular or conflicting logic, leading to unpredictable results. Instead of relying on bidirectional relationships, it's usually better to restrict filtering to one direction. If you need a reverse calculation for a specific analysis, you can use the cross-filter function in DAX. This keeps the rest of your model clean while allowing flexibility for specific cases. High cardinality columns also play a role in problematic relationships. Columns with many unique values, such as transaction IDs or customer names, cause relationships to consume more memory and slow down query performance. When possible, avoid using high cardinality columns to establish relationships. If those fields aren't essential for your analysis, consider removing them altogether. Compressing your data by reducing cardinality improves both storage efficiency and performance. Power BI tools such as Measure Killer can help identify unused or redundant columns that might be increasing cardinality unnecessarily. Many-to-many relationships are another issue often encountered in Power BI. These relationships exist when multiple records in one table correspond to multiple records in another. While Power BI supports many-to-many relationships, they should be used sparingly as they increase model complexity and can create performance bottlenecks. For example, imagine a scenario where you're analyzing sales data across multiple promotional campaigns. Each campaign might align with several products, and those products, in turn, might overlap across campaigns. Instead of building a many-to-many relationship between sales and campaigns, you can create a bridge table, a separate table that defines the unique combinations of products and campaigns. This approach not only simplifies your relationships, but also makes your model more efficient. A related issue is mismatched granularity in fact tables and dimension tables. Granularity refers to the level of detail at which data is stored in each table. A common mistake is connecting a fact table at transaction level granularity to a dimension table that aggregates data, such as monthly summaries. For example, if a sales table has transaction level data and you attempt to aggregate it using a daily calendar table, mismatched granularity could lead to inaccurate results. calculating daily averages from transaction-level data would produce skewed insights because the fact table's granularity doesn't align with the calendar table. To address this, you can summarize your fact table at the required granularity using Power Query or DAX. This ensures consistent relationships that produce reliable insights. Nested or overly complex relationships are also an issue that arises when connections between tables aren't immediately clear. For instance, imagine a model where your product table connects indirectly to your sales table via multiple intermediary tables such as subcategories and brands. While this type of chaining might seem logical in a highly normalized database, it often causes unnecessary complexity in Power BI. Users unfamiliar with the source system will struggle to understand the flow of data. Instead, flatten these intermediary layers where possible by consolidating key attributes into a single dimension table. This practice not only makes the model more user-friendly, but also improves performance by reducing the number of joins Power BI has to process during queries. Incorrect use of data types in relationships can also lead to inefficiencies. For example, linking a text-based customer ID field instead of a whole number field increases the processing burden because text comparisons require more memory and computational power than numeric comparisons. During data preparation in Power Query, ensure that fields used as relationship keys are assigned the most efficient data types. Changing a text-based field to a numeric type, when possible, will help reduce model size and improve query efficiency. There's also the issue of hidden relationships created by features like Power BI's auto-date time. This feature automatically generates date tables for every date column in your model, which can silently add complexity and consume unnecessary storage space. For example, a table with multiple date fields, such as order date and delivery date, could trigger the creation of multiple hidden date tables. To avoid this issue, turn off auto-date/time in Power BI and replace it with a custom date table. A custom date table not only consolidates all date-related attributes in one place, but also allows for custom flags like fiscal years or periods, enabling more tailored time-based analysis. This approach eliminates redundant relationships while improving both flexibility and performance. Now, you may be wondering, what's the easiest way to avoid all of these relationship pitfalls? Start by simplifying your model as much as possible. Ask yourself whether certain relationships are truly necessary or if the data can be restructured to avoid them. For instance, merging two one-to-one tables or removing high cardinality columns might allow you to eliminate unnecessary relationships altogether. Likewise, designing a star schema, where dimension tables connect directly to a central fact table, naturally reduces the risk of problematic relationships. The simpler the structure of your model, the less likely you are to encounter issues later. Properly optimized relationships lead to faster, cleaner, and more reliable models. They ensure that data flows logically through the tables without causing bottlenecks. This has a direct impact on performance, both in terms of query speed and model size. For example, eliminating redundant relationships and reducing cardinality in your model means Power BI has fewer calculations to run during refreshes. This translates into faster load times and real-time responsiveness when users interact with reports. Additionally, having a clean logical structure makes it easier to write accurate DAX formulas, reducing the risk of calculation errors. Well-designed relationships also enhance user experience. When relationships follow simple, intuitive patterns, users can navigate the model and build their own reports without needing deep technical knowledge of the underlying structure. This is particularly important when sharing your model with team members or stakeholders who need to explore and interact with it independently. A clean model empowers users to extract insights more quickly and confidently. Ultimately, optimized relationships are the foundation of any successful Power BI model. Taking the time to evaluate and refine each relationship ensures accuracy, efficiency, and scalability. If you've ever had a report that feels slow, confusing, or inaccurate, chances are the relationships in your model might be part of the problem. With a little attention to detail, you can remove these barriers and unlock the full potential of your data model. In the next section, we'll continue exploring ways to fine-tune your Power BI model by addressing its time intelligence capabilities. Specifically, we'll discuss custom date tables versus Power BI's auto-date time feature. These principles, combined with the relationship strategies we've covered here, will help ensure your model delivers the performance and flexibility you need for your reports to truly shine. Stay tuned. Taming time custom date tables versus auto-date time. Are hidden date tables silently slowing down your reports? If you haven't explored how Power BI handles time-related fields, there's a good chance this is happening in your model right now. By default, Power BI enables something called the auto-date time feature. At first glance, this seems convenient. It automatically creates hidden date tables for every date field in your dataset. These hidden tables let you quickly build time-based visuals without having to explicitly create your own date table. While this might work for simple use cases, the added convenience comes with hidden costs. Here's the problem. These auto-generated date tables consume unnecessary space, limit flexibility, and are simply not ideal for more complex or customized reporting needs. Here's how the auto-date/time feature works. Whenever you add a table with a date column to your data model, Power BI creates a hidden date table for that column. You won't see these tables in the fields list, but they exist behind the scenes, taking up model space. This happens for every date column, whether or not you actually use it in your visuals. For example, let's say you have 3 date fields: order date, ship date, and delivery date. Power BI creates 3 hidden date tables, each in isolation, instead of a single unified calendar. For small datasets, the performance hit might go unnoticed. But for larger models with multiple date columns, these redundant tables start consuming excess memory and can contribute to slower query performance. The limitations of auto-generated date tables go beyond performance. Because they are hidden and isolated, you can't customize them or extend them with additional attributes. For example, imagine you want to analyze your data based on fiscal years rather than calendar years. The default date tables don't offer you that flexibility. Similarly, let's say you want to create flags for holidays or categorize dates into custom periods. None of this is possible with the auto-date time feature because the hidden tables don't allow for such modifications. This lack of control can make it much harder to answer complex business questions that involve customized date logic. So, what's the solution? The answer lies in creating a custom date table, a purpose-built table that you design to meet the specific needs of your analysis. Unlike Power BI's hidden date tables, a custom date table is visible in your data model and fully customizable. You can include additional attributes such as fiscal periods, holidays, week numbers, or any other grouping that's relevant to your business. Importantly, building a custom date table isn't just about solving flexibility issues, it's also considered a best practice for improving model performance and efficiency. When building a custom date table, there are a few key attributes to consider. First and foremost, you'll want a column containing sequential non-repeating dates that span the entire range of your dataset. This ensures that every date used in your fact tables can properly relate to the date dimension. Next, consider adding columns for year, quarter, month, and day, so you can group and filter your data in your visuals. For businesses operating on a non-calendar fiscal year, include fiscal year and fiscal quarter columns as well. Flags for holidays or weekends can also provide additional layers of analysis. For instance, identifying whether a sales spike occurred on a holiday might help explain patterns you wouldn't otherwise notice. Constructing a custom date table doesn't require advanced skills. You can use Power Query to generate a simple table and calculate columns like year, month, and fiscal period using built-in date functions. Alternatively, if you already have a calendar table from your database or other source, you can import it directly into your Power BI model. Once the table is created, you need to mark it as a date table in Power BI. This step is essential because it tells Power BI to use this table for time intelligence calculations such as year-over-year comparisons or running totals. According to best practices, it's also recommended to build relationships to the custom date table using a numerical date key whenever possible. This reduces the computational overhead compared to using text or full date fields. Creating a custom date table isn't just about performance. It fundamentally improves your ability to analyze time-based data. Instead of dealing with isolated, unmodifiable hidden tables, you now work with a centralized consolidated date dimension. Want to calculate sales growth quarter over quarter? With a custom date table, you can easily create measures that filter or group by the fiscal quarter column. Need to exclude holidays from your sales trends? A dedicated holiday flag in your custom date table allows you to do this with just a few clicks. These additional capabilities save time and energy when building your reports. Now, let's talk about actually disabling the auto-date time feature. By default, Power BI keeps this feature enabled for all new files. You can change this setting by navigating to the Options menu under Global Settings or for specific files under Current File Options. Once disabled, Power BI will no longer create hidden date tables for every date column, freeing up memory and reducing model size. Note, however, that if you already have measure calculations or visuals relying on auto-date time, disabling the feature may break those calculations. To avoid disruption, update any existing measures or visuals to reference your new custom date table instead. While this might take some initial effort, it's a one-time adjustment that pays off significantly in the long run. Disabling auto-date time and using a custom date table also improves transparency in your model. Because the default hidden tables are, well, hidden, users don't always realize they exist. This can lead to confusion when troubleshooting performance issues or adding new fields to your model. With a custom table, everything is out in the open, making it much easier to manage and maintain your model over time. For example, if a team member inherits your Power BI model and wants to update the fiscal year logic, they can immediately see how the date table is constructed and modify it accordingly. In contrast, tweaking logic within hidden tables from auto-date time isn't even an option. Lastly, using a custom date table aligns with the broader principle of reducing cardinality in your model. Cardinality refers to the uniqueness of values in a column. Hidden date tables created by the autodate or time feature typically include high cardinality calculations like timestamps for every second of the day. This adds unnecessary complexity to your model. By removing these hidden tables and consolidating your time-based data into a simpler structure, you unlock better compression and faster query performance. For example, instead of working with a column containing every possible minute in a year, your custom date table can focus on the granularity required for your analysis, be it daily, weekly, or monthly. A custom date table provides flexibility, improves performance, and ensures cleaner, more scalable models. Whether your focus is on fiscal reporting, time series analysis, or specific seasonal trends, having a single, well-organized date dimension gives you the tools you need to build smarter analysis without workarounds or limitations. Overall, this best practice doesn't just enhance your Power BI reports, it simplifies the model for anyone else who might be using it. Tools like Power Query make it easy to create and shape these tables, so there's no reason to rely on Power BI's less efficient default approach. By turning off auto-date time and implementing a custom date table, you take direct control of how time-based data flows through your reports. And since time analysis is critical in almost every business context, the impact of this optimization can't be overstated. In the next section, we'll look at another optimization technique, reducing cardinality for better compression and performance. Just as a custom date table consolidates your time columns, reducing cardinality across other fields in your model will streamline its structure and make your reports faster and more efficient. Let's dive into how this works. Reducing cardinality for better compression. Why do unique values make your data model sluggish? This question points to an understated yet critical challenge in Power BI data modeling, the issue of cardinality. Cardinality refers to the number of unique values in a column, and it plays a significant role in determining your model's size, its performance, and even its query execution times. High cardinality columns like transaction IDs or timestamps can quickly become culprits, consuming unnecessary memory and slowing everything down. Understanding how cardinality affects your model and learning ways to address it can make a real difference in creating efficient, reliable, and fast Power BI reports. When you include a high cardinality column in your data model, like a customer ID or a sales order number, it requires Power BI to allocate storage for every unique entry within that column. This increases the overall size of your data model, leading to slower query execution and higher memory consumption when generating reports or running calculations. For instance, a sales order number may be unique for every individual transaction, which is great when tracking orders in operational systems. But in Power BI, such a field serves little purpose if it's not actively involved in relationships, measures, or visualizations. A large number of unique values can weigh down your system unnecessarily, making optimizations essential for both size and performance. Date and time data is another prime example of where cardinality can balloon unexpectedly. Columns that include both date and time components generate a huge number of unique values, potentially down to the second or even millisecond. If you're working with millions of rows in your fact table, every unique combination further increases cardinality. Combine this with the default auto-date time feature in Power BI, where hidden date tables are automatically generated for each of these columns, and things get even worse. These hidden tables not only consume extra space, but also operate in isolation, leaving you with redundant and disjointed components that harm both optimization and usability. One of the first steps to controlling cardinality in your model is to identify columns that are generating excessive unique values but aren't adding value. In cases like sales order numbers or customer-specific IDs, ask yourself, is this field necessary for any calculations, relationships, or visualizations? If not, it can often be safely removed from the data model altogether. The Measure Killer tool, for example, is useful in this context. It helps you scan your model to locate unused columns that are increasing model size without contributing to your report. Columns unused in measures or visuals are prime candidates for removal, and clearing them out can free up storage space while also simplifying your model. Another key optimization strategy involves grouping or aggregating data where possible. Consider a product dimension with thousands of product SKUs. Instead of leaving each product SKU as a unique entrance in the dimension, you might categorize them into broader product families or categories, thereby reducing the number of unique values in the column. Aggregating data in this way makes sense in contexts where highly granular detail isn't essential for your analysis. For example, instead of analyzing revenue per individual product variation, grouping products into overarching categories like electronics or apparel simplifies the data model while still supporting high-level insights. It's important to also pay close attention to the data types you assign to your fields. Proper data typing can have a significant impact on both compression and cardinality. For instance, using an integer type rather than text for columns like IDs or keys will result in better compression because numeric types require less storage than string types. If a column like a customer ID, for example, is incorrectly stored as text, converting it to an integer might reduce the model's size while speeding up queries. Ensuring all your fields have the optimal data type for their intended use is a quick, effective way to tackle the challenges of cardinality at their root. Date fields also deserve special treatment. Instead of keeping a high cardinality full date time column in your fact table, consider splitting it into separate date and time columns, or even rounding the time column to the nearest hour or minute, depending on your needs. Better yet, replace high cardinality date-related fields with references to a custom date table, which you can design with the right level of granularity. As previously mentioned, auto-generated date tables often increase cardinality unnecessarily because they operate separately for every date column, creating hierarchies for year, quarter, month, and day. Turning off the auto-date/time feature and using custom date dimensions allows you to reuse one date table for all your time-related analysis, significantly reducing overall model size. Aggregating data in your fact tables is another way to reduce cardinality and improve performance. For example, rather than storing every individual transaction, you can summarize the data to a higher level, such as daily or monthly totals. While this removes some granularity, it's often the level of detail required for most business analysis. For instance, if you're analyzing monthly sales trends over time, storing data at the transaction level offers no additional value but results in a much larger model. Summarizing your fact tables ahead of loading them into Power BI ensures that only the necessary level of detail gets included in the final model. To ensure that these adjustments create real improvements, tools like DAX Studio and Vertipack Analyzer can help you monitor your data model and assess its size and performance. For instance, Vertipack Analyzer lets you see the cardinality of every column and the storage space it occupies. A high cardinality column, such as one containing unique timestamps, will be immediately noticeable as a performance bottleneck. Armed with this information, you can determine the best course of action, whether that's grouping values, using a custom date table, or fully removing the column from your model. When you reduce cardinality, you are directly improving how Power BI compresses data. Compression is one of the key advantages of Power BI's Vertipack storage engine, but its effectiveness depends on the structure of your model. Columns with lower cardinality, fewer unique values, compress far better than those with excessive uniqueness. For example, replacing a column containing detailed timestamps with a column that tracks only the date reduces the number of unique values dramatically, improving both compression and query performance. The result is a leaner model that is easier to manage and allows reports to load faster. This reduction in cardinality not only speeds up refresh times, but also leads to more responsive visuals. For instance, applying a filter or slicer to high cardinality columns often results in noticeable lag because each selection requires recalculations across a much larger dataset. By removing or simplifying these columns, you reduce the computational load, ensuring that filters and slicers work seamlessly, even in highly interactive reports. A leaner model also means less waiting time for stakeholders when generating insights, creating a better experience for end users. The benefits extend to writing DAX as well. A cleaner, simpler model with fewer redundant or high cardinality columns means you can write more straightforward DAX formulas. Instead of complex workarounds to handle large, unwieldy datasets, you can focus on creating measures and calculations that add value. For instance, calculating total sales by category is faster and more intuitive if the product dimension groups items into manageable categories rather than thousands of unique SKUs. These performance improvements cascade throughout your entire workflow, from model creation to delivering insights to stakeholders. High cardinality columns are a common problem in Power BI models, but they don't have to be the Achilles heel of your reports. By identifying unnecessary fields, grouping or aggregating values, and applying proper data typing, you can drastically reduce cardinality and improve compression. The ripple effects of these optimizations include faster queries, smaller model sizes, and more responsive interactions, ultimately making your data easier to analyze and your reports far more effective. When it all comes together, reducing cardinality creates a streamlined Power BI model that isn't just faster. It's scaled to support better decision-making, whether you're analyzing millions of rows or just dozens. This foundational step ensures the rest of your model operates efficiently, setting the stage for faster calculations, smoother visuals, and genuinely insightful analysis. And these improvements tie closely into the next topic: how reducing model complexity makes DAX even more powerful and easier to use. Let's take a closer look at how this optimization directly impacts your ability to write better, faster DAX in the next section. The real-world payoff of proper modeling. What's the ultimate reward for all this effort? If you've spent time building a proper Power BI model, you might not immediately see the benefits until you start using it. But the truth is, a well-structured model transforms the way you analyze data, drastically simplifying the process, speeding up reporting, and creating consistency in your insights. A good model lays the foundation for effective reporting, and once it's in place, everything else becomes easier. Let's think about the alternative for a moment. Without a clear structure, your analysis quickly becomes overwhelming. Messy models lead to slow reports, confusing tables, and wasted time trying to figure out why numbers don't add up. Missing relationships or unnecessary complexity will leave you chasing errors instead of focusing on insights. Imagine trying to analyze sales data only to find that your total revenue numbers don't match when filtered by product or region. These kinds of frustrations are all too common when models are thrown together without planning. What should be a straightforward process ends up taking far longer than it should, which slows down decision-making and creates frustration for both analysts and stakeholders who depend on accurate reporting. One of the most noticeable benefits of a strong data model is how much easier it makes analysis. A clean, performant model speeds up your reporting by eliminating inefficiencies. When the relationships between tables are properly designed, you avoid long load times and poorly optimized queries. Think about how much faster it is to generate a report when your tables and columns are already structured logically. Instead of waiting for filters or slicers to process unnecessarily high cardinality columns or complex relationships, your queries run smoothly and return results almost instantly. This directly impacts productivity. Time saved here can be spent focusing on deeper analysis or delivering actionable insights. Another huge advantage of strong data modeling is the way it simplifies DAX calculations. Writing DAX is often intimidating for beginners, and even experienced users can struggle with complex logic in poorly optimized models. But when your data is organized with fact and dimension tables in a simple star schema, DAX becomes much more straightforward. For example, calculating total revenue, year-over-year growth, or sales per region is easier when all the necessary information is clearly structured. A well-designed model simplifies DAX calculations, making them easier to write and maintain. And this reduction in complexity not only enhances report performance but also saves time when creating or updating measures. Take real-world scenarios as an example. A retail company with hundreds of thousands of daily transactions needs to analyze sales trends and forecast future revenue. With a poorly designed model, their analysts might spend hours cleaning up relationships in Power BI or writing overly complex DAX measures to account for missing dimensions or inconsistent granularity. A single report could take hours or even days to build and validate. Now compare that to a structured model. The fact table holds just the essential transaction metrics, dimension tables provide necessary context, and relationships are clear and logical. Building the same report now takes significantly less time, as calculations like monthly sales or regional trends are easy to configure and reliable every time. Proper modeling also supports faster decision-making. When your model is optimized, you can quickly pivot from one question to the next without running into performance bottlenecks or unintentionally breaking measures. For decision makers, this is invaluable. Instead of delaying strategic moves while teams dig through messy data, they can point to well-structured reports and make timely decisions. In competitive industries where speed matters, being able to trust your reports saves critical time and gives you an edge. This process also removes barriers in collaborative work. Data models are a foundation for teamwork, especially in larger organizations. A poorly designed model creates friction. It's harder for others to understand the structure, troubleshoot problems, or add new calculations. But with a clean, well-documented model, everything flows more easily. Whether someone else is taking over your reports, collaborating on a dashboard, or adding new data sources, a logical, consistent structure ensures they can pick up where you left off without needing to unravel a tangled web of tables and relationships. Another area where data modeling skills transfer is with new tools like Microsoft Fabric. Fabric is an evolution of analytics tools that focuses on advanced data workloads, tying in AI and machine learning. Success with Fabric, like Power BI, depends heavily on understanding data modeling principles. The ability to lay out a clean star schema, reduce redundancy, and optimize table relationships isn't just a Power BI specific skill. It applies across modern analytics environments. The skills gained from mastering data modeling transfer to tools like Microsoft Fabric, making you better equipped to adopt new technologies and adapt quickly as tools evolve. This adaptability is a major asset for career growth as organizations increasingly rely on interconnected data-centric tools. The empowerment that comes with mastering data modeling can't be overstated. When you build strong foundational models, you gain confidence in your ability to work with data. That confidence carries over into your ability to take on larger, more complex projects. For example, once you've structured a reliable sales analysis model, tackling something like customer segmentation or supply chain optimization becomes less intimidating because the principles remain the same. You know how to approach the data, identify relationships, and design a structure that works, no matter the specifics of the project. This kind of empowerment is why data modeling is a skill that elevates your entire career. A good model doesn't just benefit you, it directly contributes to business success. Organizations rely on data to guide their strategies, and clean, performant models ensure that the right insights are available at the right time. Building a robust foundation for reports and avoiding common performance issues enables businesses to respond quickly to changing circumstances, identify new opportunities, and avoid costly mistakes. For example, An e-commerce business can use a well-modeled report to assess the impact of a promotion in real time, slicing data by geography, product category, or customer segment without delay. This kind of agility drives better business outcomes. For individual professionals, mastering data modeling provides tangible career benefits. It sets you apart as someone with the technical skills to not only analyze data, but also design systems that make analysis easier for everyone. This kind of expertise is highly valuable in roles like data analysts, report developers, and business intelligence specialists because organizations depend on scalable, maintainable models to manage increasing data complexity. A well-structured model also acts as a portfolio piece. You can showcase your report-building skills, the logic of your data design, and the performance of your outputs as evidence of your expertise. Career growth isn't just about technical ability. It's also about becoming a trusted contributor to business success. A high-performing data model earns you credibility within your organization because people know they can rely on the information it provides. This credibility leads to higher impact projects, leadership opportunities, and long-term career momentum as the demand for data-driven decision-making continues to grow. The payoff for proper data modeling is clear. It simplifies analysis, saves time, and reduces frustration for both technical users and the business teams relying on their work. With more reliable insights, businesses can move faster, make smarter decisions, and ultimately drive success. For professionals, the ability to design clean, structured models is a game changer that opens doors to new tools, better opportunities, and powerful contributions to their organization. Everything you've learned about data modeling, organizing your fact and dimension tables, avoiding pitfalls with relationships, and optimizing performance sets the stage for becoming not just a better Power BI user, but a more capable data professional overall. These skills are the foundation of analytics. And while they might seem technical at first, their applications reach far beyond the tools. With every well-thought-out model you create, you're sharpening your ability to communicate stories, solve problems, and simplify complexity in a way that benefits everyone. In the next part of this video, we'll reflect on the data modeling journey you've just explored. Whether you're just getting started or refining your existing skills, the principles we've covered aren't just about fixing mistakes, they're about building habits that elevate your entire practice. By mastering these foundational techniques, you'll not only create better models, but unlock greater potential in everything you do with data. Let's tie this all together in the final section. The most important thing you can do in Power BI is start with a strong data model. As Mitchell Pearson explains, a well-structured data model is the foundation upon which all successful Power BI reports are built. Without it, report performance suffers, insights become harder to derive, and even advanced DAX skills won't save your analysis. Take time to review your models. Look at relationships, cardinality, and the structure of your tables. Which areas could you simplify or optimize? Start applying what you've learned today. A solid data model doesn't just improve your reports, it transforms how you work with data entirely.